Hello and welcome to Intro to Chem Lecture A. So we'll get started. What is chemistry? Chemistry is the study of the properties and structure of matter. So first we should probably talk about what matter is. Matter is anything that has mass and takes up space. Has mass, takes up space. That's pretty much everything around you. It's hard to remember that gases are also matter, but they are. They do have mass. They will take up space. They fill up a balloon when you blow up a balloon. So we're basically going to be studying everything. We're going to study how they're shaped, how they're formed, what they're made out of, how we put those pieces together. We're also going to talk about their properties. About the only thing around us here on Earth that's not matter would be energy. But energy is one of the properties of matter, so we are basically going to study everything this year. Because there's so many different compounds out there, so many different elements, chemists have a shorthand way of writing all of those names and showing those interactions. And one of the first things you're going to learn how to do is use their chemical symbols. Now, the element names are not based on their English names. The element names are based on their Latin names, and some of those can be confusing. So let's take a look at your periodic table and reference table S. So if you get your reference tables out, one of the last tables on your reference table is reference table S, and it looks like this. Now all the elements on reference table S are listed according to their atomic number. Now this is the most important number because it tells you the number of protons in the nucleus of an atom. If, for example, we look at carbon, so that's element number 6. On your periodic table in his square, this big bold number, the most important number, is the atomic number. It's going to identify which element you have. Notice that some of the names don't seem to make sense for the name of the element, like sodium is Na, and again, remember, it's based on their Latin names. While we're here, we're going to talk about how we write these symbols. 1, 2, or 3 letters. The 3-letter ones you're not going to find on table S, 1 or 2 letters in the symbol. The first letter is always capitalized. Now we're talking capital letters, not just big letters. Capital letters and lowercase letters. The one that shows up a lot that people have problems with is sodium. This is not a capital N and a lowercase a. That's a really big lowercase n and a small lowercase n. Don't write that. This is a capital N. This is not a lowercase a. That's a capital A, just small. Don't do that either. They have to look like the ones on the table. That's how we know when an element starts. If I look at a compound, like this one, and I see 1, 2, 3 capital letters, I know it's made of 3 different elements. So it's really important that you get the capitalization correct. We're going to put them into combinations with subscripts. Subscripts are going to be small numbers below the line, and you've done this before. So CO2, carbon dioxide, or CO, carbon monoxide. Di meaning 2. See the 2 down here? Mono meaning 1. See the 1 down here? So you don't see the 1 because it's just like math class, where you can write 1x or you can just write x. The little subscript always goes to the element that's right in front of it. So 1 carbon and 2 oxygens. You learned other ones in biology like glucose, C6H12O6. Water you usually know coming in, H2O. We also are going to talk about energy this year because one of the properties of matter is energy. So energy is going to be defined as the ability to do work. Basically, we're going to make stuff move. We don't typically think of everything around us as moving all of the time, but the individual molecules and the individual atoms of the things that surround you right now are all moving. So kinetic and potential, you probably remember. Kinetic energy is going to be the energy of motion. So a slinky shows both elastic potential energy, because when you stretch the spring out, it gives it potential and it wants to go back into its original coiled up shape. And when it moves back to that coiled up shape, that's kinetic energy. You're also going to see gravitational potential energy when you play with a slinky. Because of its position here on the top step, As it starts to fall over, gravity is pulling it down, and because it's moving, the motion is the kinetic energy. Over here, the girl has the ball and she's holding it up. So she has created potential energy because she's holding it above the earth, and gravity's pulling down on it. As soon as she takes her hands away, gravity pulls it down, and that motion is kinetic energy. Here in chemistry, we're going to look at some of the smaller ones. So gravitational and elastic potential energy, pretty much physics. We're going to talk about those things in physics. In chemistry, we're going to store potential energy within the compound itself, so they call that chemical potential energy. The forces holding two atoms together to make a molecule. So in water, the force that holds the two hydrogens to the one oxygen, that's going to be your chemical energy. We can also store electricity. So electricity is moving electrons, flowing moving electrons. In a battery, we have chemicals where there's extra electrons that want to flow, and we prevent them from moving, so that electrical energy is now stored within our battery. Most of our talk about energy is going to be in kinetic energy. We're going to mostly talk about thermal energy. So when we're talking about energy in chemistry, the kinetic energy we talk about the most is going to be thermal energy, also called heat. So we're going to measure the average kinetic energy in a substance, okay, how much those particles are moving, how much heat is produced. We're going to measure heat in a unit called joules. That's going to be with a capital J. And the potential energy that we talk about most in chemistry is going to be this thing that we call bonds, or bond energy. So when we have that water and you have one oxygen and you have two hydrogens being held onto that oxygen, your bond energy is the force right here that holds this one hydrogen to this oxygen. So we're going to transfer it from one form to the other, always moving from one form to the other, and that is going to be this law of conservation. This law of conservation of mass and energy becomes very, very important in chemistry. It's going to show up a lot. Energy is neither created nor destroyed. Matter is neither created nor destroyed. If it took me 100 joules of heat to melt something, then if I want to freeze it, I'm going to have to release 100 joules of heat to freeze it. So if I'm absorbing it, it's going to be equal but opposite to freeze it. Absorb it to melt it, release it to freeze it. Always the same amount. If I'm making water and I have a hydrogen molecule and an oxygen molecule and I'm going to make water, I need two hydrogens for every one oxygen. There's two oxygens here though. Where does that other oxygen go? In order to account for it, in chemistry we do this thing called balancing. We say, well, if there was two oxygens here in the first place, I'm going to have to make two water molecules. Okay, so basically when I put that capital 2 in the front, it's like saying I've made two of these. So now I have two oxygens, but now I have four hydrogens. So I have to put a 2 here because that's like saying I have two of these hydrogens. So now if I have two hydrogens and one, remember if we don't see a number, we assume it's a 1, and one oxygen, I can make two water. The only time that that's different is in nuclear chemistry. Einstein figured out that you can turn very small amounts of mass into very large quantities of energy. Very, very large. Nuclear weapons, nuclear explosions, nuclear power plants. And what he calculated was that if you took the speed of light, let's check this out, 299,792,458 meters per second. That's a huge number. Light's moving extremely fast. And when you take a really large number and you square it, you get an even bigger number. It takes a very, very small fraction of mass to make a huge quantity of energy. We are taking a lab-based science class, so there will be measurements and calculations. Don't worry about the calculations because we're talking algebra here. One of the differences, though, is that we will be using decimals and not fractions. That's the biggest difference between math and science. In math, you're talking about imaginary numbers. In science, we're talking about measurements. Okay, so you're working with imaginary fake numbers in math. They're really, really precise and accurate. 1/2 or 1/3. Your math teachers want you to use these numbers because they are precise. This little line actually means to divide. So you're talking about 1 divided by 2, which means not just 0.5, but 0.5 with an infinite number of zeros after it. 1 divided by 3 is 0.3, but not just 0.3, 0.3 with an infinite number of threes. In science, we're talking about measurements. We don't have any instrument that is accurate to an infinite number of decimal places. In science, you have to show how accurate your instrument is. So there's going to be a difference between writing 0.5 and writing 0.50. Okay? There's a big difference between these two things. It's called significant figures. That's in Lecture B. It shows how accurate the instrument is. We also have to use a scientific calculator, and this is different from math. In math, you use your graphing calculators. We have to use a scientific calculator, and we're going to use scientific notation. This EXP button down here, EXP, that's the one that you're looking for. So on your scientific calculators, when you want to do scientific notation, so some number times 10 to an exponent, the button you're going to use is EXP, or on some calculators, it's EE. Sometimes it's a button, sometimes it's a second function, and what it's going to do, when I hit this button, it's going to put in the times 10 to part for me. So if I wanted to put in 5 times 10 to the second on a scientific calculator, I do 5 times 10 to, so the EXP is your times 10 to button, and then I hit the equal, and I get 500, because that's what this means. Times 10 to the second, positive integer, you're going to move that decimal point over 2 places, so that number really means 500. We'll practice using the scientific calculators in class. I'll show you the different ones that we have. We have 2 different ways that we collect data, both qualitatively, and that's just using our senses. Is it hot? Is it cold? Is it soft? Is it hard? Is it red or blue? And quantitatively, and most of us know that quantitative has something to do with quantities, with numbers. So if I were qualitatively looking at this rose, I would say that that rose is red. If I were quantitatively going to give a measurement, I would say that the wavelength of light given off by the petals is, say, 650 nanometers. You can say it's hot, and that also is objective. Some people, a hot day is 80. For some people, it's not hot until it's 90, and it has to be humid. So it is a qualitative description. If you get a thermometer and say it's 98 degrees Fahrenheit or 37 degrees Celsius, then you have a quantitative number. Temperature is one of those things in chemistry that we can grab a thermometer and give a quantitative number to. We are also going to try and be very precise in our work. So there's a difference between accurate work and precise work. Accuracy tells you how close to the actual number you get. What we really care about this year is being precise. You want to learn the lab techniques. You want to use the same piece of equipment the same way every single time. So for example, you know in a graduated cylinder, the proper way to read it is to read the bottom of the meniscus. So you get at eye level and you read where the bottom of the meniscus is. If every time you use a graduated cylinder, you're getting down at eye level and reading across the bottom of the meniscus, you're being very precise. Well, to figure out our accuracy, we do something called percent error. You've probably done this before, percent error, percent deviation, experimental error. I learned it as the experimental value minus the actual divided by the actual times 100. My teacher also taught us to do the absolute value here. Now the only difference between doing the absolute value or not, the number will be the same. The only thing that's going to be different is the sign in front of it. If you follow this equation without the absolute value bars, a positive error tells you your number was greater than the actual. A negative error tells you your number was less than the actual. Now, equations are on the back of your reference table. The very back page is reference table T, and we have the percent error equation there. And where I learned it as experimental and actual, the state is calling it the measured value. What did you measure during the lab? And the accepted value, what are scientists saying is the real number right now. So the example we have here, if the accepted value of the density of aluminum is 2.7, and I measured the value be 3.1, what's my percent error? So we plug those in. 3.1 minus 2.7 divided by 2.7 times 100, 14.8%. A quick word about lab work. Students always want to know, how good is my data? How low should my percent error be? Oh no, my percent error is 85%. It's fine. In college, your college professors might give you a value that they want, usually less than 10% error, because what we're going for is not accuracy but precision. It really doesn't matter what your percent error is. What's more important to me is if you get an 85% error, double check your calculations with me. Sometimes you've just missed a step. If your data says you have 85% error, then go back in your observations and your notes and see if you can explain to me why you have an 85% error. So don't panic if you have very large percent errors. It's just going to happen in some of the labs because of the equipment that we have. All right, that wraps up Lecture A.